Good morning, gang. As I said, I'd like to introduce to you Chapter 12 today. I'm not going to take the entire hour. I'm up early in the morning here on Wednesday. Want to give you an introduction to Chapter 12, and we're going to go ahead and just get started on this. Chapter 12 is reaction kinetics. We've just finished the unit on energy, the energy involved in reactions. We saw Chapter 6 telling us how heat is involved in reaction, flowing in or out of a system. And then Chapter 17, which got us into entropy and the delta G. This is really strange. I'm looking at myself as I teach, and I'm not used to that. I have an empty classroom. But when we get into Chapter 12, I told you a couple of times in Chapter 17 that when we determine the delta G and we determine whether a reaction is spontaneous, that does not tell us how fast the reaction goes. That's a different study. The reaction is going to be determined, whether it happens or not is determined by the delta G. But how the reaction happens is what we talk about in Chapter 12, reaction kinetics. That's what my first slide is. What is kinetics? And the notes are posted on Schoology. I hope that you're following with that. What is kinetics? Kinetics, as we saw kinetic energy in Chapter 6, is the energy of motion, how fast something is going, goes into kinetic energy. So in thermodynamics, we talked about state functions and how enthalpy, entropy, and delta G are state functions. Thermodynamics deals with the beginning and the ending state. Kinetics is what's going on in the middle. This is a graphic that we use frequently in both delta G and kinetics problems or situations that determines, it doesn't determine, it describes how much energy the system has as it proceeds. So we have reactants here. The reactants will go through some process. Remember, we talked about how in order to have a rearrangement of atoms in a reaction, energy needs to be put in. And so the reactants have to break apart. There is an increase in energy as the system takes in energy to break the reactants apart. The bonds break, needs to have energy put in, and then energy is given off as new bonds form. So the reaction will decrease. The system will decrease in energy until it gets to the products. Now what we see on this graphic is an endothermic process because the products have more energy than the reactants had. If it was an exothermic process, the products would end down here lower than where the system started. So a graph like this, we'll see this a number of times. Well, kinetics deals with what's going on there during the process of the reaction. What's causing the reaction to go fast if it's fast, and what's causing it to go slow if it's a slow reaction. That's what we're going to talk about here in the next couple of weeks. So as you see on here, the kinetics has two components to it. How fast is the reaction going, and what are the steps? What is the reaction doing as it goes from reactants to products? Now there's two ways. We talk about the rate of a reaction, how fast a reaction is going. Rate is always a change over time. So there's two different ways for a reaction that we can determine. And really it's the same thing, but two different things that we can measure. You can measure how fast the reactants are being used up or how fast the products are being made. So the reactants get used up, there's going to be a negative change over time because the reaction concentration is going down. Or as the products are being made, how fast are the products being made, the concentration is going up. So the rate, the rate's always going to be positive. If you have a means for measuring how fast the reactants are getting used up, that negative, we're going to have to put a negative sign in front of that expression to make the rate positive. But if we're measuring how fast the products are being made, that's a positive slope, we would use a positive value here. often, I'll say most of the time, in when we start talking about rate laws and we start actually quantifying reactions, we'll usually look at how fast the reactants are getting used up. So you're going to see that negative sign there quite a bit as we deal with the reactants. Now this is a seemingly harmless slide, but this is going to be very useful to us and applicable as we do problems. We know the balancing of an equation. I'm just making up a generic equation here. A yields B plus 2C. The coefficients in a reaction we know very well as the relative amounts. As B is made, C is made in twice the quantity because we have a 2 coefficient for it. When we're dealing with the rates as well, the coefficients are going to indicate how much the rates are changing compared to one another. So as A gets used up, its concentration goes down. As B gets made, of course, its concentration goes up from 0 at the beginning. And C is going to be made twice as fast as B is made. So the coefficients do give an indication of, okay, we're going to make twice as much of C as B, but also C is going to be made twice as fast. So the rate of B and the rate of C are related by that coefficient as well. So that's what this slide is describing there. Coefficients determine the relative meaning compared to one another, rates of the reactant consumption and product formation. I want you to remember that too from this slide. There will be exercises. This seems, as we go through this, seems so very simple. I think all of us can agree, yeah, if we have a 2 in front of the C, that means that C will be made twice as fast as B. It's intuitive. However, when you get to the problems in the exercises in the book, you're going to see, you'll be asked about this kind of thing, and a lot of times students they just get dumbfounded. I don't know how to, if they're giving us the rate of one thing is X, you need to know that C would be 2X. And you'll be surprised at how you'll just lose that in your thinking. So yeah, we'll have to come back to that sometimes during this chapter. We're going to spend a lot of our time in chapter 12 looking at something called a rate law. In science, a law will represent a relationship. A rate law is it's a mathematical equation that's going to describe a couple of things about the rate of a reaction. It describes it describes how fast a reaction is going and how the concentration of the reactants affect the rate. So the concentration, the more concentrated a reactant is, the faster the reaction will go. So there's two different ways, two different types of rate law, two different ways of describing how fast a reaction is going. We can either vary the concentration and see how it affects the rate. If we do that, we'll be able to write what we call a differential rate law. And then we can also determine how the concentration of a reactant is changing over time. That's known as an integrated rate law. So there's, again, a law is a mathematical relationship. There's two different ways to measure rate law. There could be more than two ways, but in chemistry, these are the only two types of rate law that I've ever learned, differential rate law and integrated rate law. As we do, and this is, I know this right now is just words, I'm going to have a lot more detail. Like I say, we'll spend a lot of the chapter looking at these two different rate laws and what they look like and what they tell us, what the terms mean. Every rate law, though, is going to involve something called an order. The order of the reactant. The order is going to tell how the concentration of the reactant is affecting the rate, and that will vary. We do know, we can make a general statement that the more concentrated the reactant is, the faster the reaction is going to go. However, if, um, sorry, I was just making sure, as you saw me walk up to the computer, I was making sure that I actually had started the recording on it. We're good. Um, so, yeah, the order is going to tell us how fast, or not, how the concentration is affecting the rate of the reaction. In different reactions, the reactant concentration affects the rate differently. And that is going to be described by what the order of the reaction is. The order of the reactant. Okay, one thing that we need to understand, this middle bullet point here is so important. For a reaction, we always have a chemical equation that describes the reaction. And the equation is going to have coefficients. Coefficients are not the same thing as the order. You know, if I have something like hydrogen plus oxygen yields water. If I have a 2 coefficient there and a 2 there, it does not mean that the order of hydrogen is 2 and the order of oxygen is 1. Just because we have coefficients here does not necessarily mean that's what the order is. Now again, we haven't even seen what order means. I have a cursory description of the order here. But I just want you to know that you don't get the order just from looking at the coefficient. We get the order by running the reaction in several different trials, varying the concentration of the reactants, and the rate of the different trials is going to tell us how the concentration, as we change it, is affecting the rate of the reaction. So yeah, the order tells us how the concentration affects the rate. It is not necessarily what the coefficient. Sometimes it is the coefficient, but not always. So we need to run the experiment and find what the order is of each reactant. Now, I do mention there's 2 different types of rate law. The 2 different types of rate law vary differently in the way that they look. The differential rate law has a certain look to it. The integrated rate law has a certain look to it, and they're not the same at all. But they do give us similar information. Okay. So we're going to start with, I want to show you generally what a differential rate law looks like, but then we're going to focus the rest of our time today on what an integrated rate law is. We're going to do 2 labs in this chapter. One of them, we're going to determine the integrated rate law for a reaction, and then the other one, we're going to determine the differential rate law for a reaction. So we'll have a chance to do both. I'm going to start by introducing the look of the differential rate law. So here's an example. We have a simple reaction, a decomposition reaction, N2O5 breaking down into 2 smaller things. I need you to just bear with me. We have run the experiment several times, varying the concentration of N2O5. This is fictitious, of course, it's generic. But we're going to just say that our experiment shows that this reaction is first order for the N2O5, first order. What does that mean to be first order? Well, if we write the differential rate law in its first order, what that means is, this is what the differential rate law would look like. The rate of the reaction is equal to K, some constant value, and K will vary from one reaction to another. It's K times N2O5, the reactant concentration, to the first power. That power represents the order of N2O5. So if we have run an experiment, we've determined that the N2O5 is first order, then this is the way that the rate law would look. It's always, if it's a differential rate law, it's going to have rate equals. That part's always true. And the rate is going to have the same unit all the time. It's molarity per second. Rate is molarity per second. Just like your rate of speed would be meters per second or miles per hour. Some change over time. K is called the rate constant. Again, it changes for every reaction. And there's several things that go into the K value. We'll spend time on K. But yeah, then it's K times the concentration of N2O5 to the first power. So the order is what the exponent is on the N2O5 concentration. Really what I want you to see on this slide, though, is just what the look, what a differential rate law, how it's written. There it is. So when you see rate equals K times the concentration to a certain power, that is going to be the look of a differential rate law. We'll spend a lot of time on these, but not right now. I'd like to show you the integrated rate law and what that looks like. Again, integrated and differential look very different from each other. This one is differential. Now, you see the word integrated. If you are in the calculus class, you've done lots of derivatives and integration by now. The integrated rate law is literally going to involve an integral. Now, if you are not yet in calculus, you have never learned about integrals, don't worry about it. I'm actually going to show you why it's called the integrated rate law. This is like most derivations we do in here. You're not responsible for the derivation, but I do want you to see how it works and why it's called this. So, okay, we're working with the same chemical equation, N2O5 decomposition. We've run the experiment. We find that it's first order reaction. So if it's first order, that means that the concentration of N2O5 is a first power relationship with the rate. Meaning this, the rate of change of N2O5 over time, how N2O5's concentration changes over time, is, according to the differential rate law, K times N2O5 to the first power. Now, if I monitor this reaction and I look at it over a time interval, at any point in that time interval, we would have this change. Now again, this is for the calc students. Algebra 2 students, just smile and bear with me and make yourself look like you know what I'm talking about. And you can smile and nod your head like, yeah, okay, this is fine. Again, I'm not asking you to do this. But what we have here is change in N2O5 over time equals K times N2O5. Again, it's first order. We had to determine that with an experiment. If I were to take the N2O5 terms and put them all together, I had change in N2O5 and I had the concentration of N2O5 to the first power. Put those on the same side of the equation and put the time term on the other side of the equation. It would look like this. Notice I would have to divide out the N2O5. It's going to be 1 over concentration of N2O5. Oops. Times negative D of N2O5 equals, and moving this dt term over to the other side, K times dt. I'm going to take that negative sign and push it over here. It could be either side. I'll make it over on this side. So yeah, what I have here, I'm going to do this in this little space. Just make this look like this. 1 over concentration of N2O5 equals, I did it again, times D N2O5 equals negative K dt. If I integrate both sides over some time interval from 0 to t, integrating both sides, calc students, you'll remember what the integral of 1 over x is. It's the natural log of x. So what I'm going to have, and now I'm going to need some room. This is going to come together. Even if you're in calc, you may not be following. What is he doing this for? I'll show you here in a second. But what we would have is, we would have the ln of the concentration of N2O5 at time t minus the ln of the concentration of N2O5 at time 0. we have it over that time interval, equals, over here on this side, the integral from 0 to t of just dt, you know, the k would, making sure my screen is active there, the k is a constant value, so it could go outside of the integral. So it would just be kt, negative, got the negative sign here, negative kt. It would be time at time t minus at time 0, which we would just leave out because it's times 0. So yeah, this is the integral of both sides of that relationship. Now, we normally will put it into this form, ln of concentration N2O5 equals negative kt plus ln of N2O5 at time 0. So I just took this term here, the minus ln of N2O5 at time 0, moved it over to the other side. Okay, now what did I just do? What did this mean? I have a mathematical equation that describes, again, this is first order, and for any reaction which has a first order reactant, the integrated rate law, as long as it's first order, is going to have this pattern. The variables here are the concentration of N2O5 at some time t. Whoops, what did I just do? Sorry about this. Looks like the TV just turned off. I don't know why it didn't. Oh. Nuts. I have never seen that. Wouldn't you know, it's when I'm recording something. Okay, hopefully I can get back on here. I'm going to stop mirroring. Oh. I asked you on the first day of school to be patient with me with the technology. Sometimes this stuff just happens. Let's see if I think it is an Apple TV fault. Oh man, I'm up a creek if I can't have this. Don't do this. I can try to punt and figure out something else. Just bear with it. I'm so sorry. Oh, I don't want to do that either. Okay, so if I try to play this from the computer. Okay, so yeah, maybe it was a connection between the iPad and the computer, but we can figure this out. Okay, so I'm just going to do this. Man, I hope this turns out okay. I don't want to redo this. I was just here, and yeah, so we had seen that, and I have it on the next slide. So if we go now to slide 8, this is what our integrated rate law looked like for this reaction. The natural log of the concentration of the reactant, if it's first order, equals negative kT, K being a constant, T being time, plus the natural log of the initial concentration of N2O5. So this term is a constant. The K value is a constant. So what we have here is a changing value. As the reaction proceeds, the concentration of the reactant is changing. Over time, so the time is a variable as well, it's changing. The K and the initial amount are constant. So what we have here is we have a relationship that is a linear relationship. It has the form y equals mx plus b. The y term is this, the natural log of N2O5. The x value is the time. And so we have a slope of the line given as negative k. I actually have that wrong there. Negative k is the slope of the But the magnitude of K really is what I'm getting at there with that, is the slope. So down here what I have is in red, this red term, after all the kind of gibberish that I was just going through to derive this, it really comes down to this. If you have a reaction that we determine is first order in the reactant, the reactant is a first order reactant, what that looks like is if we take the natural log of the reactant concentration and plot it versus time, you'll get a straight line, as long as it's first order. Now there are other orders. You can have a zero order reactant, you can have a second order reactant, you can have a third order reactant. It's not common to have other orders, but yeah, natural log of the reactants versus time is a straight line if it's first order. Okay, now I'm not going to burden you with the order of the other reactants. And if you'll allow me, I'm going to just try this one more time on the iPad because there are other things that I'll be writing. Oh, this is going to work. Okay, good. Okay, I'm going to come back to this. So good, we were here, and we're going to move on. If the reaction is second order, now I'm going to use a different reaction. It's just a generic A yields B reaction. So for a general pattern of a reaction, A is the reactant, B is the product, whatever they are. If we run an experiment and we determine that A is second order, I'm not going to do any more integrating. I'll just go in. I think if you're a calc student and you're really fascinated and interested with integrating the world, you can do this yourself. It's not difficult, it's simple integration. If it's a second order, that means that the rate is K times A squared. That would be the differential rate law. Well, K times A squared would be the rate of the reaction, which the rate is how the concentration of A, the reactant, changes over time. Now, if you integrate that relationship, you're going to get this expression that comes out of it. 1 over the concentration of A equals positive KT plus 1 over the initial concentration of A. This again is a second order reaction. Second order meaning that the A had a squared term. In this integrated rate law, I want you to see that the K, again, is a constant, called the rate constant. The A0 is a constant. Now we're taking the inverse of the A0, but it's a constant value. So the concentration of A is changing. We have the relationship between the inverse of A and the time. If time is plotted on the x-axis again, the inverse of A would be the y-axis, and it would be a straight line, because this follows the pattern y equals mx plus b. So if it's a second order, if you graph the inverse of the concentration versus time, you'll get a straight line. If it's zero order, I have that on the next slide. Oops, whoops. Sorry about this. I tried to take care of all these formatting things before. So yeah, I've got a kind of a falling math expression there. If sometimes you can have a zero order reactant, which means that the concentration of the reactant does not affect the rate. The rate is going to be the rate no matter what the concentration of that reactant is. Zero order does not mean that there is none of the reactant. It means that the concentration of the reactant does not affect the rate. So, if you have a zero order, the rate is equal to K times A to the 0 power, and zero order means, I've already said what zero order means. If we integrate this, so the rate again is how the concentration of the reactant is changing over time. Integrate that relationship, which we can do. K times A to the 0 power is just K. But if you integrate both sides, you're going to get this relationship. So you see that even if you don't have any idea what integrating is, depending on the order, this mathematical expression is different. For zero order, it looks like this. Just the straight up concentration of A versus time looks like this. If it was second order, the inverse of A versus time looks like this. And if it was first order, the concentration, or the natural log of the concentration versus time looks like this. So in summary, again, I know at the beginning this is really strange. In summary, really, here's what we need to know. And if you haven't followed any of my rationale for any of these, I think that you can wrap your brain around this slide. This is slide number 11. I'm only going to do up to slide number 12. This 12 is an example. And I think the example is going to help us a lot. So we don't really understand what order is yet. That's going to be developed as we go through the chapter. But if you have a zero order reactant, that means that when you make a graph of the reactant concentration versus time, if that gives you a straight line, that tells you that it was zero order. If it was first order, that means that when you graph the natural log of the reactants versus time, that's going to be a straight line. And the other graphs would be not straight. If it was second order, a graph of the inverse of the reactants versus time is a straight line. So I keep mentioning these graphs. Do we really need to do the graph? Yes, we need to do the graph. So I'm going to finish with an example. And my example is on the next slide. This is taken as a photograph right from the book. I don't know if I have what number this is. Ooh, the formatting on this one is weird. I don't think let's see. Give me a second. Oh, I know what I mean. There. Yeah, I was thinking. I had the question number covered up here by my data. This is number 37, taken right out of our book. So it says, in number 37, it says, the decomposition of hydrogen peroxide was studied, and this data were obtained at a particular temperature. So they're watching how the concentration of hydrogen peroxide, the reactant, is changing as it decomposes. It says the decomposition of hydrogen peroxide. So over the period of 20 minutes or so, they're monitoring the concentration of H2O2. So as we see how the concentration changes versus time, that's going to give us an integrated rate law. If we go back to, gosh, the third slide, I think, fourth slide maybe. Oh my gosh, it did it again. I apologize. I just got kicked out. I don't know if I'm touching something that it doesn't like. Okay, here we are. Nope. Yeah, the integrated rate law is where we look at the concentration versus time, and that's what number 37 is doing. It's giving us, okay, as the time goes on, what is happening to the concentration? It's going to allow us to find the integrated rate law. Now it says down here, if you want to determine what the order of hydrogen peroxide is, we can't tell from just looking at this. We see that the concentration is going down, but what is the pattern? What is the trend for it as it decreases? That we're going to have to make the three graphs. And what I'm talking about is here. I'm going to have to plot the concentration of hydrogen peroxide over time. Then I'm going to have to graph the natural log of the concentration versus time, and then the inverse of the concentration versus time. I'm going to graph all three of those and then determine which one is the straight line. The one that gives me the straight line is going to be which one the correct, it's going to tell us what the order of the reactant is. Okay, so what I did was I made a graph. And I'm going to now change this. I'm going to take the smart board there behind me and switch it to the computer. Okay, there it is. Oh, you don't want to see that. That's weird. But I made a graph. Took an Excel spreadsheet. And I want you to notice here, I have in the A column the times. I just copied down the data. The time and the concentration of H2O2 is given. And then I have in the column C, I took the natural log of those concentration values. So the natural log values are there. And then in column D, I took the inverse of the concentrations. And so then I made three graphs. The first graph was, as the time changes, how is the concentration changing? And let's take a look at what that graph looks like. So notice the title of the graph here is just straight up concentration. H2O2 concentration versus time is graphed. And it looks like this. You can see this is not a straight line. And that tells me that this reaction, whose data was given to us, is not a zero order reaction. That's what we do. We actually graph the data. If it's a straight line, that means it was that order. If it's not a straight line, in this case it's not. It's not zero order. So then I will look at the graph of the natural log of the the natural log of the concentration versus time. Now let's take a look at this one. This looks like it's pretty linear. Now, how linear is it? We're going to also take a look at I'm going to try to put them side by side. This is the first order graph where I'm taking the natural log of the reactants versus time. It's pretty straight. This is the second order graph where I'm taking the inverse of the concentration versus time. Now notice this one has a positive slope because as the concentration goes down, the concentration's in the denominator, so that fraction goes up. So yeah, the second order graph is always going to have an upward trend. I think it's very obvious in this case what the order is. The order is first order because the natural log of the concentration versus time is a straight line. Sometimes two of your graphs will both look fairly linear. Something that we can do on our Excel program is the iPad is going to be different, but if we right-click on one of the data points, we can get to, we'll get a menu. And if we go to Add Trend Line, we can have the Excel make the line of best fit of the data. And you can see this is what is dashed here is a straight line. And then we can also give something called the regression. It's the R-squared value, linear regression. And Excel will tell us what the R-squared value is. This is a mathematical thing. It's super handy for when you're having to look for trends in data. If R squared is 1, it's exactly a straight line. And the closer R squared is to 1, the more linear the data is. And you can see that this R squared value is 0.9998, very linear data. But we can tell that. We can tell this one's linear and the other two aren't. So we can tell that it's a first order reaction. The hydrogen peroxide decomposing reacts in a first order kinetics pattern. So in summary, and I'm just going to get rid of this stuff. In fact, I'll just go back to this. So let's see. Okay. The question, the book is actually asking us to do is in this part. If you're looking at your notes document, it says determine the rate law, comma, the integrated rate law. So if they say just the rate law, they mean the differential rate law. which again, I'm not going to focus on differential until later. But we just used this data to determine what the integrated rate law was. We had to do the 3 graphs in order to do that. You see that that's how we figure out what the order is. We have to make the 3 graphs of the concentration versus time, the natural log of the concentration versus time, and then the inverse of the concentration versus time. One of those is going to be straight, and that tells us what the order is. So that allows us to figure out what the integrated rate law is, and then it says the value of the rate constant. The rate constant, remember, is the slope of that line. The K value is the rate constant. We're going to work on those when I get back on what day is that going to be. Thursday we're going to go over the test, and then Friday we'll go over how to find the K value, and we'll actually do that. I just wanted to give you an introduction to what the rate law is and how we find it. Even if this, you walk out of here thinking, well, that was a recording, I wish he never did that. I don't understand anything he just said. I will pick this up on Friday, and I think that with another example or two, and we'll go through the mechanics of how to find the K value and what it means and that kind of thing. It will come together. You did need to see this little introduction first. Be patient with this. Be patient with me. Trust me that that I'll get you there if this is still kind of fuzzy. So have a wonderful Wednesday, and I will see you tomorrow.